That's what makes sense to me, but it doesn't really state that explicitly.
It's impressive how many of you are here today, almost like a complete class. I thought I might be lecturing to an empty room or just to the television, but this is nice. Towards the end, I have some homeworks to return. And all right, so we have obviously one lecture this week left. I mean, today. There's no lecture Friday. There's no discussion section tonight. I put that on the web, but let me reinforce that. And then we have 2 weeks after this one, which means 6 more lectures. One of those, at least, will be given by somebody else. So I have to try to figure out what topics fit well with the times that are given. So I'm going to try to do something that's complete today, a little bit out of order. But we've pretty much finished all of our discussion of NP completeness and approximation methods and different ways to respond. We are going to talk a little bit about randomized algorithms, which would have been natural to include at this moment. But I think given the way the time is chopped up, we'll defer that. And so what I'm going to talk about today is linear time string matching. So you should at least see once, if you haven't already seen in your undergraduate years, some linear time string matching algorithm, because it was one of the classic results in algorithmic computer science, and very surprising when this was first developed. Okay, so the problem is that we're given a string, S, and we're given a text, T, and we want to find all the occurrences of S in T. Okay, and the elementary operation that we're going to use in counting in considering algorithms is a character comparison. Whenever you look at 2 particular characters, you ask whether they're equal, whether they're unequal, whether if there's an ordering to the alphabet, you might ask whether one comes before the other in the alphabet. Various questions like that, but those are character comparisons, and that's what we're going to consider. So let me give you, well, I mean, I think everybody solves this problem in one form or another almost every day, right? Whenever you're looking through something in text and you're looking for some particular piece of it, or anyway, I don't think I have to motivate the problem. But the obvious way of solving this, if you have here a very long text and here have a short string, the straightforward approach to solving this is that you would put the string here against the text, and then something like that. And you would start comparing whether these 2 characters are the same, and if they are, then you move on to the next one, and if they're the same, you move on to the next, and if you get to a place where they're not equal, then this string did not occur in the text, at least starting at that position. On the other hand, if you were able to do the comparisons all the way through, like that, to the end of the string, then you know that the string occurs there. And whether it occurs there or doesn't occur there, what you do next is you slide the string by 1 position and you start over. You would compare this character to that character and so on. Now, if the string is, let's say, of length n and the text is length m, then the worst case analysis for this very simple approach would be something like big O of nm compares. At every position, there are roughly m different positions where you could put the string. And at every position where you put it, you would do roughly n comparisons. Sometimes fewer. You might mismatch on the first one. But we could certainly rig up examples where you would do actually roughly that amount of comparisons. I mean, for example, suppose that the text was all A's and the string was all A's. Then the string matches the text at every position. And with this direct approach, this simple algorithm, you would actually be doing n comparisons at every position. And there are m minus n positions, but m is bigger than n by quite a bit. So at any rate, that many comparisons. And we could even, as I said, we could make it tight like that. So that's the naive approach. And for emphasis, this is a multiplication of n by m. I'm putting the multiplication in there. And m can be huge. M can be in the billions in many applications, or even bigger. And n can be in the hundreds or thousands. And if we're talking about applications from databases or biological databases, for example. So, when you have your typical paper and you're looking for some small string in it, you could do something naive and it would work okay. 10-page paper and a string of length 7 or 8. You could do this kind of direct comparison. I mean, it's actually useful to write a program that does this directly and start pushing up the sizes of the problems and notice that it will break down in fairly small values of n and m. But for huge values of n and m, it's certainly not going to be workable to multiply n times m. So in the early 1970s, I guess, I'm not sure exactly when, but it was first discovered that you could solve this problem in n plus m time. That many operations, that many comparisons. So it's a very small change because you just take this symbol and turn it 45 degrees. So it's nothing to it, right? Very minor. But it had a huge impact because, well, this is quite a bit smaller than that. And actually the first discovery of this was Don Knuth and some others on the Knuth-Morris-Pratt paper. And he has a very interesting history of how he discovered this. It was sort of accidental because they were all conjecturing that this was not going to be possible, that this was a time bound that was much too small for this problem. Well, since that time, there are many different algorithms that achieve this. And what I'm going to show you today is a particular algorithm that I think is the simplest and fastest way to get to that result. And it also has a lot of other applications. So I need some definitions before we do the algorithm. And for string s and a position I, zi s is going to be defined as the length of the longest substring of s that starts at I and matches a prefix of s. Okay. So let me give you an example. Here's, let's say s is equal to A, B, C, B, X, Z. Okay. So just to exercise the definition here, Z of 2, I'm going to drop the S in here. So Z of 2 is equal to 1. Okay? So the longest substring that starts at position 2, so we're starting here, the longest substring that starts at 2 and that matches a prefix, which means starting at position 1. The prefix of S starts at the left end, position 1. The longest substring that starts here and matches a prefix has length 1. It's just this single character A. A matches A. This substring, it's starting at position 2, begins AB, and the prefix begins AA. So the longest match is just a single character A. Okay. Let's do some other ones. Z6. Okay, this is 1, 2, 3, 4, 5, 6. Starting here, what's the longest match starting here that matches a prefix? That's also length 1, right? Because this substring begins ABX and this begins AA, so the match is just a single one. Z9, let's try that one. 6, 7, 8, 9. Now we have, starting here, the substring is AAZ, and the substring, the prefix here again is AAB, and so on. So the longest match here now has length 2. It's the AA. So Z9 is equal to 2. And all the other Z's, I guess, are just 0. For example, Z7, it begins with that substring begins with a B, but the prefix begins with an A, so that matches length 0. Okay, so that's the definition of Z's. And we're going to have something called Z boxes. So here's just a representation of S, and this is position I, and this is called a Z box. And really all this means is that starting at here, we have a ZI greater than 0. So this is the substring. This is the longest substring that starts at I that matches a prefix. So this substring in here, I might call it alpha, and then therefore this is an alpha. So ZI is greater than 0. It means there is a substring that starts at position I that matches a prefix, and I'm just want to give it a representation. Okay, call it a Z box. Now, the interesting thing is that, let's say this is character X. What's this character? So the character that immediately precedes this Z box is X. What can we say about this character? It's not X. Whatever it is, it's certainly not X, because the definition of ZI is that it's the longest substring that matches. So this is not X. Whatever it is, it's not X. Okay, it's X X'd out. Okay. All right. So we can draw Z boxes to show where we're finding values of ZI greater than 0. And when we have a Z box that starts at position I, I'm going to designate its right end. Sorry, is RI. And yeah, okay, so that's the right end. Oh, okay. Well, so by the way, the notes that I'm reading from here, I've posted on the class website, so you can. It's not in the book, but you can look them up there. All right. So the algorithm is going to compute all the ZI for I equals 2 all the way to the end, and I should have, this is S and T. Now, in this whole discussion of the Z algorithm and computing Z's, this S is not just the pattern, it's just an arbitrary string. Okay, so maybe it would have been better to have had here a pattern, use P for a pattern, because typically that's this application for pattern inside a text, whereas S here is just an arbitrary string because we're talking in generality. Okay, and I'll relate S to P and T in a minute. But we're going to compute all the ZI for I from 2 up through the length of S. And so before I show you how to do that, and we're going to do this in time that's proportional to the length of S. Okay. So before I show you how to do this, let's look at how this, if you had this ability, how that solves this problem, the problem of finding all occurrences of the pattern P inside text T. So to find all occurrences of a pattern P in T, you form S equals P. Sometimes it's convenient to put something in the middle that's definitely not in either of these, some symbol that's not in either P or T. So, but it isn't actually needed, not in P or T. So I form this S, which is the pattern concatenated with some new symbol concatenated with the text. And then compute all the Zi values. So I'm claiming we can do this in time proportional to the length of S, which means it's time proportional to the length of P plus the length of T. And that's the M plus N. It's the plus in there. OK, now how do you use these? Suppose you had computed all these Z values. How would you use this to identify where the pattern occurs inside the text? Any?
I have C and D, and the index is length of P plus length plus 1 for that character. Then if it is equal to length of P, then I can say that there is a prefix of P that matches T.
OK, you might have gotten some things in there just slightly backwards, but I can see that you have the right idea, which is that if you, here's the P, and the dollar sign, and then here's T. Now the Z values you compute in here are useful later just for getting these Z values. But suppose you find a Z box here, OK? So this is Zi, and it happens to be equal to the length of P. What does that mean? It means that this substring that begins here at position I, but we would then have to figure out what position that actually is in T, but that's just the length of I. That's I minus the length of P plus 1. So we know it. That's just arithmetic. If Zi is equal to the length of P, it means that this substring here, by definition, is equal to a prefix of that length of this S, which means it's equal to the pattern P. Okay. Now, if Zi was less than P, then we would not have found an occurrence. And Zi cannot be bigger than the length of P because of this dollar sign. That's really the only purpose of putting it there. Well, it also helps in computing some of the Zi's here. They won't extend beyond this point, because, again, this is a symbol that doesn't occur anywhere else in there. So it just keeps things a little conceptually cleaner. So everybody see this? That if you could compute all the Z values in this concatenated string, then all you have to do is look for those Z values in this range that are equal to P. And that would precisely tell you where inside the text are you seeing occurrences of P. And then to report those occurrences, you just have to do some arithmetic on the index. Okay. So if we can compute all the Z values in linear time, in time proportional to the length of P plus the length of T, then we can certainly report all the occurrences of P and T. So we're actually computing something a little bit more general, that is all the Z values, which solves this problem, but can be used to solve other problems as well. So the key thing is, how do we compute all the Z values in an arbitrary string S in time proportional to its length? And I've started the algorithm here. It says for I equals 2 through S. So we're going to do it in that order, in fact. Okay. I equals 1 is, of course, not interesting, because by definition, it's just the whole string. There's nothing to do. All right. So let me start developing the algorithm for how we're going to compute all these Z values. So the algorithm. First of all, for I equal 2, we're going to find Z2 by direct character comparisons. That just means we're going to look at the pattern and look at the string. No, we're back in S just as an arbitrary string. Okay, it means we're going to look at, here's S, here's position 2, here's position 1. We want to know what's the longest substring that starts at position 2 that matches a substring that begins at position 1. And we can do that by just direct comparison, by the two-fingered algorithm. One finger at the start of the string and one finger here, and we ask whether these two characters are the same. If they are, we move on. If they're the same, we move on, and so on. And as long as we can keep matching, then we keep moving. So that's 1 match, 2, 3, 4, mismatch. So Z2 here is equal to 4, right? Substring there, 4 A's, equal to the substring there, which is 4 A's, and yet we can't continue. So Z2 is equal to 4. If you think about it, there's actually a special case when, for 2, Z2 is a special case. The value of Z2 is actually equal to the number, the length of the longest run of identical characters that are identical to the first one, minus 1. Okay? Because again, if you just think about the algorithm, for Z2 to be greater than 0, this character's got to equal to that character, so that's a run, beginning of a run. And then when you move on, this character's got to be equal to that character, so that's a continuation of the run, and so on. So anyway, Z2 can be computed directly by just doing comparisons of characters. And the total number of comparisons to compute Z2 is obviously bounded by the length of S. I claim we want, in the end, to compute all the Z values in time in the number of comparisons bounded by the length of S, or proportional length of S. Okay. So it doesn't look good right now because we've already spent, in worst case anyway, just to compute Z2, we're already, since we're doing this directly, we're already doing a number of comparisons which in worst case could be the length of S. But don't worry, we can do everything else for free. All right, not quite, but anyway, we'll do everything else and still be within the same bound of S, even though on the very first iteration it looks like we've used up all of our time. All right, so now assume inductively that we've computed, so assume that Z2 up through Z I minus 1. I just want to make sure I'm consistent with the notes here. Well, okay, K minus 1. The notes, we're using an index K. K minus 1 have been computed. And also assume that we know what is the farthest Z box that's been found so far. What's the Z box that extends furthest to the right? So this is the farthest right extending Z box found so far. So far in the algorithm. And R is going to be its right end, and L is the left end of that particular Z box. It's the Z box, so that Z box is between L and R. Okay? So this is S again. All right, so we're going inductively and we've computed zk minus 1. And now we want to compute zk. And possibly change R and L, depending on what we find. Okay. So what we do is going to depend partly on what k is compared to r, and some other things. So I need to move over to a clean board. So the easiest, or the easiest case to describe now is, I'm in 2. I probably lost contact with the numbering in the notes, but at any rate, let me just call this 2A. If k is bigger than r, so what does that mean? It means we're in this picture, k is somewhere out here to the right of r. There's no z-box that has extended as far as k. All right? And so what's happening is that we have very little information, therefore, about k and anything to its right. So the algorithm is just going to do direct comparisons here as well. If k is greater than r, then again, compute zk by direct comparisons of the substring k up through the length of s and 1 up through the length of s. So it just means one finger goes at position 1, one finger goes at position k, and we're just going to look at those characters. If they're matching, we keep moving, and we keep moving until they mismatch, and that certainly will compute zk because it's done directly. Nothing tricky here. Okay? Later, we'll have to ask about the time it's taken to do all this, because if you do this direct comparison for every k, you're really going to be in big trouble, and then your time bound is going to be quadratic. It's like s squared, not s. But certainly in terms of correctness, this is certainly an okay thing to do because you're explicitly doing comparisons. All right. Now another case is k is less than or equal to r. Okay, so let's look at in understanding this algorithm, pictures are the most helpful thing. So everybody internalize the definition of zi? All right. So here is where we can start taking advantage of the fact that we've already computed some of these values. So here is the rightmost z-box, and now we're saying that k is less than or equal to r. K falls in that z-box. Okay? So I'm going to use alpha here to denote this whole string, and I'm going to use beta to denote this substring at the end from k to r. All right, this is s. Now, we certainly know by the definition of a z-box, so there's a z-box, we know there's another copy of alpha here at the beginning of s. That's what a z-box means. It means that starting here, there was a match, a substring here that matches a prefix, okay, and this is as long as possible from here. So definitely alpha is here. Therefore, there's another copy of beta here that I can draw. Which one is that?
Starting inside the alpha.
Inside this one, yeah. So yeah, since this all alpha certainly equals that alpha, therefore, this beta must be inside there as well. So that's a copy of beta. All right? And, all right. Now, the next character over here is an x. Let me just say x, okay? What can we say about the next character here? It should not be an x, right? Because, I'll just call it a y, where y is not equal to x. And the reason is that, we discussed that earlier, if this was equal to x, then in fact, this z box should have been longer. Okay? So we know these two characters are in fact not equal. All right, so what can we say? Yeah, what can we say about? So we want zk. All right, and we're looking at this picture. Oh, I see. Okay, yeah. So now let me call this one k prime. We can do arithmetic. I could fill out, tell you the arithmetic to tell you exactly what this index is, but let's not. Okay. I mean, obviously, given L and R and K and so on, I can tell you what k prime is. Certainly, there's some value here, which is index here, which is the beginning of this copy of beta. All right. So we have this picture, and we want zk. And so now I'm going to break down another case. So let's call this 2bi. And zk prime less than beta. So the algorithm, remember, has computed the z values left to right. So we know what zk prime is. We're way out here. We were trying to compute zk. And we certainly already know what zk prime is. And so we've got this general picture. Suppose we look up zk prime, and we find out that its length is less than beta. Okay? Then tell me what we can conclude. Yeah.
The length of zk is also less than beta, because
That zk is what?
the length of zk is also is equal to the length of zk prime.
Right. Okay. So yeah. So if that, then zk is equal to zk prime. Why is that? Well, we know that from this point forward, at least to here, we have beta, which is identical to what we have from k forward, which is beta. And what we're interested in is what's the length of the longest substring starting here that's equal to something starting here. But we know that starting here, that length is less than the length of beta. So let's say it's like that. Okay, this picture is getting a little cluttered. So this is beta here. And these are, maybe I'll call this gamma. These two are identical. But then there's something else here, like a p, and something here where p is not equal to q. And over here, we must also have a gamma at the beginning. This whole thing is beta. And this additional character here, we know that has to be a p. So because this zk prime is strictly less than the length of beta, we know that, well, we know what I just said. So here we have gamma followed by p. Here we have gamma followed by q. Here we have gamma followed by p. And therefore, zk is identical to zk prime. All right? So this was a very nice case because we don't have to do any character comparisons at all. All we had to do was say, I want zk. I compute what k prime is. I look up k prime. We already have it. I compare it to the length of beta. If it's less than the length of beta, then I already know that we have this identity. and no additional comparisons are needed. Okay, so we got ZK for free. You have to go through this by yourself. I mean, the picture is helpful, but you really need to go through those steps to convince yourself that all this works. But if there's any questions here, let me, so if somebody can point to a place where they don't see the step, let me know. Okay.
I'm missing the part where I don't see why ZK prime can be less than beta. I mean, because we said that from K to R is beta.
From K to R is what?
Length beta.
It's called beta, yeah.
Okay. And so we're saying that that has to match where K prime to Y is negative.
Yes, that's also beta. But what we need to know about is how much does this agree with something that's at the beginning of S.
Okay.
We know how much it agrees with this beta. It agrees all the way to beta. And then it mismatches. But we don't know how much it agrees with what's at the beginning. But that, if ZK prime is less than beta, then we know that that's a case where, in fact, we do know how much it agrees. It agrees by exactly that much. It agrees by ZK prime and no more. So in that case, in this case, we don't have to do any character comparisons. So did that answer your question?
Yes. Thanks.
Okay. All right, so let's do another case. And you'll see when you look at the notes, not only are these numbers different, but I've kind of divided up the cases a bit differently too. But it's the same ultimately. So let's take the case that I might call it 2B double I. If Z K prime is strictly bigger than the length of beta. All right? So again, look at the picture. I know it's kind of messy here. Now ZK prime is strictly bigger than the length of beta, which means at the beginning here, this gamma, which goes out to there, it goes out past the length of beta, and then it has the next character, which must be y. It must be identical to that, because ZK prime is bigger than beta. It's bigger than this piece. Over here, ZK is, that substring starting at K consists of beta, but now followed by an X. So comparing to what's going on at the beginning here, we have identity for length beta, but then we have a Y here and an X there. So what can we say about ZK now? Yeah, ZK is equal to beta. All right, so we had another case where we didn't have to do any actual comparisons. Right. So ZK prime is strictly less than beta. We get ZK for free. If ZK prime is strictly bigger than beta, length of beta, we get ZK for free. It's equal to beta. And so the only case that's left is ZK prime equal to beta. Maybe I should redraw this picture because it's getting very cluttered. Oh, let's over here. So again, we have the alpha. And now we have K prime. And here's beta. And we know that ZK prime is equal to beta. So we have a beta here at the beginning, but the next character over, we knew that was a y, where y is not equal to x. So that's our picture. We have ZK prime equal to beta. What can I say about this character? It's not y. Whatever it is, it's not y. Okay? But it might be x. There's nothing to say that it's not x. All right? I mean, there's nothing that we can get from our information that we have in hand to say that this might not be x. So in fact, zk might be bigger than beta. So all we know at this point is zk prime is greater than or equal to beta. And what the algorithm should do, therefore, is do some direct comparisons, comparing this character to this character. If they're different, then we know that zk is equal to beta. But if they're the same, then we should keep moving over and do direct comparisons as long as we can. Okay? So in this case, now do direct compares to find zk. And also, if we find out that zk is in fact bigger than the length of beta, then we adjust R and L. Okay, if you find out, let's say this is an x here, so we have that matches, and maybe we have a p and a p, but then we get a z and a w. So what happened was that zk is equal to the length of beta plus 2 in this little example, and therefore we found a z box that goes past where the other one was. So we move over R, because R is defined as the rightmost z box, and we move over L, because L is the length of is the starting point. We never really used L. L is just used to figure out k prime whenever you want to actually turn this into a program. So when we find that zk is strictly greater than beta, then we adjust R and L also. We note that this is the rightmost z box. Okay, and that's it. That's the algorithm. So correctness. Well, here we did direct comparisons, so it's explicit whenever k is bigger than R. And in particular, we started with 2 when z2 was done directly. So that's right. In the case that zk prime, in the case that k is less than or equal to R, then we had these 3 subcases. Zk prime is less than beta, and we argued that this was a correct deduction, so I'm not going to repeat that. When zk prime is bigger than beta, and again, we're in that the 2 case, then we argued this was a correct deduction. When zk prime is equal to beta, we argued this was a correct deduction. And from that point forward, we're doing direct explicit comparisons. So again, we can't go wrong. So the correctness here should be pretty obvious. All right. So let's look at, oh, and I guess I should have said one thing more. When you do the direct comparisons in this case, in 2A, then if zk, if you find that that's bigger than 0, then again you adjust R and L. Okay? Because you're actually finding a z box out there to the right of what had been your previous farthest right z box. So you're always adjusting where the rightmost z box is that you find. All right. In the other 2 cases, you're not changing the z boxes at all. You're not changing what the rightmost z box is in this case and in this case. Right? The z box, the rightmost z box point doesn't change. R doesn't change. Ooh. Okay, time analysis. So that's correctness. Time analysis. We're counting the number of comparisons. In some iterations, we don't do any comparisons. Well, those are easy to take care of. I mean, those are the cases where, like the 2B, this case and this case, we don't do any comparisons. We only do comparisons in this case. This is 2B3, and over here. All right? And here's the key point. Well, the key observation. If we have, let's say, Q matches when computing ZK. So we're actually doing some character comparisons, and in some iteration where we're trying to compute ZK. And those character comparisons have Q matches. The key point to notice is that R moves by at least Q. It increases by at least Q. Then R increases by at least Q places. In this case, when you're doing Q matches, R moves by exactly Q. Okay? I mean, this is the case where we're here, we're looking at this character and this character, and they match. And this was where R was. This is one character to the right of R. And we're doing those matches. And however many matches we do, Q of them, R moves over. The new R is here. So it moved over by exactly Q. In this case, K could be quite a bit bigger than the existing R. And when you do some matches, then R moves to K plus Q, or K plus Q minus 1. Anyway, it can move even more than Q places past the previous R. But it certainly moves by at least that many. There's no place in the algorithm where R ever decreases. Okay? So, and R is never bigger than the length of S. R can't go beyond the length of S. So the total number of matches in the whole life of the algorithm is less than or equal to the length of S. Okay? Well, whenever you do a comparison, it's either a match or a mismatch. So we've counted for how many matches there are. How many mismatches can there be? Well, again, in some iterations, we don't even do any comparisons. But in those iterations where we do a comparison, that iteration ends as soon as we find a mismatch. If we're doing direct comparisons here, we're doing character by character. The first time we find a mismatch, the iteration is finished. And the same thing over here. The first time we find a mismatch, the iteration ends. So the total number of mismatches is also bounded by the length of S, as that's the number of iterations. There's one iteration for each position in S. And also, so this is also mismatches less than or equal to S. All the other work in the algorithm is proportional to the number of iterations. I mean, in an algorithm, in an iteration, you're looking at K versus R. That's one thing. If you're in this case or you're in that case, and then you look up ZK prime, you do a little bit of arithmetic to find out what K prime is. You look up ZK prime, you do a comparison. So all of that's constant per iteration. Therefore, the amount of work you do there is proportional to the number of iterations. That's therefore proportional to the length of S. And so we've done it. That's the whole time analysis. The algorithm does work which is proportional to the length of S. The number of operations is proportional to the length of S. So we've done what I claimed we can do. We can compute all the Z values in time proportional to the length of S. We can use that to solve the problem of looking for all occurrences of P inside T, as I explained earlier. And another on-time arrival. OK, so we have a few minutes to pass out homeworks. This is homework 4. I apologize, homework 3 is, I'm still not finished with it. I should have let the TAs handle it all. They're much more efficient than I am. Kevin Liu. OK. Anho, right there. Chen Kai Chen. Tyler Martin. No. Kristen is not here. Jason Honda. Okay. Eric Pernice. Yep, he's here. Dustin Pluta. Eric. No, you're not Eric. You're Eric. Sean Williams. Nope. David. There you are. Eric Stolzberg. Shi Yan.